So it turns out you can't pause the video. You have to stop it and start a new one, which I've done. Hopefully I won't have to clear my throat again. Let's go ahead and put our numbers in here. QO is our 2 nanocoulomb charge. Nano means times 10 to the minus 9. Now I've got my VB, 8.476 times 10 to the 5 volts. Subtract my VA, 1.199 times 10 to the 6 volts. Gives me a change in electric potential energy of minus 0.07.03 times 10 to the minus 4 joules. So my electric potential energy decreased. Okay, part C, how much work is done by the electric field as a 2 nanocoulomb charge moves from A to B? Okay, so we have that motion. We know what the change in the potential energy is. So let's see what the work done is. So part C, we know that our work done is negative the change in potential energy. And negative the change in the potential energy is positive 7.03 times 10 to the minus 4 joules. So there's my work done as that charge moves from point A to point B. Okay, let's do another type of thing next. So next, well, we've already looked at what if we have 1 point charge. Now let's ask what if we have multiple point charges. So let's say I have 3 point charges, 1, 2, and 3. Now how would I figure out the electric potential and the electric potential energy at point P? Well, if I have multiple charges, I have multiple sources for the potential. So to find the total potential, I would just add them all up. So at point P, Q1 is going to make a potential. So my V total at point P is going to be the potential due to charge 1 plus the potential due to charge 2, because that makes a potential, and charge 3 also makes a potential. I have to add them all up. My potential due to charge 1 is K times Q1 divided by R1. R1 is my distance between my point and my charge, plus my potential due to charge 2, KQ2 over R2. R2 is between my point and my charge 2, plus my potential due to charge 3, KQ3 over R3. So that's how I would find my total potential. As an equation, I might say that my general equation, my total potential at some point P would be the sum of K times the individual charge divided by the individual distance. So you would add all those up and get your total potential. The electric potential energy, if we place a charge QO at point P, then it's going to have a potential energy equal to the charge, QO, times the potential at that point. So if you know the potential to find the energy, you just multiply by the charge. Okay, why don't we do an example like that next? And we'll build off of our previous example. So I have a 1 microcoulomb charge placed at the origin, that's Q1. A 2 microcoulomb charge placed at x equals 0.75 centimeters and y equals 0. Here's my Q2. And I'm going to go through my questions. What is the potential at points A and B? This one's going to be just a little bit more work. The potential at point A will have a contribution due to Q1 and a contribution due to Q2. It'll have 2 parts. So this is my Q1. This is my Q2. And I'd like to find the potential at each of these points. So at point A, my potential at A is my potential due to charge 1 at A plus my potential due to charge 2 at A equals K times Q1 over R1. Why don't we even put in an A there so we're not getting so confused. So here's the distance between charge 1 and point A, plus K times Q2 divided by R2 and A. Here's my distance between charge 2 and point A. So now I think I'll just go ahead and put in the numbers here. So the numbers you put in 8.99 times 10 to the 9 for K. Q1 is 1 times 10 to the minus 6. R1A is 0.75. R2A, that was our 1.0607 centimeters. So we already found that number. When I crunch all those numbers in, I get 1.199 times 10 to the 6 volts plus 1.695 times 10 to the 6 volts. So my total potential at point A turns out to be 2.894 times 10 to the 6 volts. That's my potential at point A. I also want my potential at point B. So VB is V1B plus V2B. That's going to be K times Q1 divided by R1B plus K times Q2 divided by R2B. Let's just get those numbers in our picture. So the distance between 1 and B, R1B, is from here to here. That's also 1.0607 centimeters because it's just the diagonal of the square. Between 2 and B is my 0.75 centimeters. So when I do this calculation, I get 8.476 times 10 to the 5 volts plus 2.397 times 10 to the 6 volts. And my total potential at B turns out to be 3.245 times 10 to the 6 volts. So that's my total potential at point B. Okay, part B. What is the change in electric potential energy if we take a 2 nanocoulomb charge, I'll call that QO again, and we move it from point A to point B? So we'll put our charge QO right here, and we'll move it from A to B. So part B, we're asked to find delta U equals UB subtract UA equals QO times VB minus QO times VA equals QO VB minus VA. You could also write that as QO times delta V. So QO times VB minus VA, we know all those numbers. QO is 2 nanocoulombs. VB we just found. Subtract VA. And we get for our delta U 7.21 times 10 to the minus 4 joules. So that's the change in potential energy as we go from here to here. We notice that's positive. Part C asks what's the work done. That's the negative of the potential, change in potential. So negative 7.21 times 10 to the minus 4 joules. That's a negative work done by the system to get it to move from A to B.